All right, so I know you saw a little bit of this in lab yesterday. We're just going to kind of reiterate it. The pH scale is something that we use to help us to describe the acidity or basicity of a solution. And the pH scale ranges from 0 to 14. On the 0 end of the scale, we have stuff that is extremely acidic. On the 14 end of the scale, we have stuff that is extremely basic.
Now, I would say 7 only, right? 7 only.
Okay, so
There was a problem at 7.2 and I put neutral and it said wrong.
So yes, if we take it from a literal standpoint, 7 is neutrality and everything else is either acidic or basic. If we take it on a practical sense, then what we consider neutrality is usually like from somewhere between 6.5 to 7.5. That would cover things like the water that we drink, our blood, most things that we would consume. Other things would fit on one end of the scale or the other. So, coffee, for example. Coffee is acidic. pH of coffee somewhere between 4 and 5 usually. Sodas. Yeah, I'm listening.
So I thought acid and sour.
Yes.
So why is coffee not sour?
Well, so coffee can be sour. I mean, if you have old coffee that's been sitting around, the bitterness goes away and right. Yeah, there's an oxidized factor in there. Now, what you have to consider, coffee is a large combination of substances. And so the prevailing substances in there include a number of alkaloids, and the alkaloids are bitter tasting. So the majority of the flavor is not coming from the acidity, it's coming from the other compounds that make up this very complex group of substances that are in coffee beans.
But since shouldn't it sour? Yeah.
Well, again, it's a little bit more complex than that. It's not just, we're not dealing with just an acid in there. Acids themselves are sour, yes. You take citric acid, you take absorbic acid, you take hydrochloric acid, and you put them on your tongue, they will taste sour. But coffee is more than just an acid in water. And so there are going to be other flavors in there. And it's those other flavors that you taste. Now, going back to my cold old coffee example, when those compounds that are responsible for the bitterness degrade, then come through the more acidic flavors because those other ones have degraded. And that's where you can taste the sour acidity of that coffee once some of those other compounds have broken down. But before then, those bitter compounds have a much stronger impact on your palate than the sour flavors do. So the problem is when we're looking at these properties, acid properties versus basic properties, we're looking at acids on their own versus bases on their own. When we talk about mixtures, we have to understand that there's a lot more to a mixture than just one substance usually. Right?
pH of 2.
Right.
Sour.
Yes.
But I mean, there's
Right. So in lemons, in any citrus, you've got a large combination of acids, and they all have a strong sour flavor to them.
So it's the compound.
Yeah, and so even though, you know, even though their pH may not be as low as, say, a hydrochloric acid or a sulfuric acid, the fact that you've got a combination of them and they're all present and doing all the things that they do to your tongue, that's going to bring that sour kind of impact. So again, pH is just a measurement of how much H plus ion is present in that solution. It's not necessarily a measurement of sourness or bitterness or any other properties that we usually associate with acids and bases. We're just, when we talk about those acid-base properties, we're talking about broad descriptions of those substances. Bases in general are bitter. Bases in general feel slippery on your fingers. Acids in general taste sour. You're not gonna find a whole lot of common thread looking at, you know, pH and sourness and trying to make many links between the two. It has as much to do with the identity of the acid as it does its concentration, as it does the strength of the acid. There are many factors that go into those. All right, so again, kind of taking the pH scale literally, any pH less than 7 would be considered acidic. Any pH greater than 7 would be considered basic. Now again, we can talk about the acidity and basicity in practical terms and probably find that neutral is more of a range rather than just a strict value. But if we take it literally, that's what it means. Now, all of this is based upon the concept of the concentration of the hydronium or the H plus ion. And what we have to remember about all of that is that we can calculate the pH of anything by taking the opposite of the logarithm of that H plus or H3O plus concentration. H plus, H3O plus, they're the same thing. Basically, we're just talking about in H3O plus, we're talking about the interaction of that H plus with water. So kind of looking at the Arrhenius versus the Bronsted-Lowry definitions of acid. Same thing, same idea, just slightly different interpretations. Did you do pH calculations in lab yesterday? Okay, so you've seen kind of, there are 4 equations that are useful as far as calculations go. And if you ever wanted to turn it around, so let's say that you were given the pH and you wanted to figure out the H plus concentration. Then what you would use are called the antilogs, where you just take 10 to the negative power of whatever the pH is. So there aren't many calculations on these slides related to that, and you aren't going to find any in the homework. But that's all that you would need to do. So just for example, if you had a pH that was 3.5, if we wanted to try to find the H plus concentration, we would take 10 to the negative 3.5 power. Now, depending upon your calculator, you know, I have a Casio model. All Casios look pretty much the same when it comes to the way that you calculate. So usually you can find the anti-log function as the opposite of the logarithm function. Now on my model, you always have to put in the number first and then the function. If you have a TI calculator, then you would just type it out completely. But for me, so it's negative 3.5. So I got to put 3.5 in, and then it's shift logarithm. And so the concentration of the H plus would be 3.16 times 10 to the negative fourth. Now, like I said, as far as what I've been asking you to do in terms of the homework, that's actually a level of question that I kept pulling out of the homework because it didn't look like it was showing, it wasn't in the original slide deck, and it also wasn't in the version of the lab that I saw that you were doing, because it looked like you're just using pH paper and then calculating backwards from that. Well, since the pH paper is all, whole numbers, 10. Yeah, so if you've got pH 3 on your paper, 10 to the negative third would be the concentration. 1 times 10 to the negative third. So that's kind of, now, if you've got a TI calculator, does anybody have one that I can just borrow real quick? Yes. So, if you've got a calculator that looks like this, or similar, and again, all the Texas Instruments calculators kind of have the same look, the same functionality. It's also the opposite of the logarithm function here, but unlike mine where you had to put the number in first, second logarithm, negative 3.5, you're going to get the same number. The only difference between this one and this one, mine was put into scientific notation. This one wasn't. That's the only difference. So, kind of looking ahead to what you might see on your lab quiz, because I don't know. That would be the only thing that you would have to do. As far as, like I said, one of the reasons we're not having a dynamic module for chapter 10 is because these kinds of questions were just peppered throughout that chapter 10 module. So I couldn't get up to the minimum to let that one happen. So if we're answering questions like this, identifying solutions as acid, basic, or neutral, well, it all comes down to pH. And if I'm given the pH, it's pretty easy. So HCl pH 1.5, 1.5 is definitely less than 7. So this is an acid. pH less than 7 again with the Sprite, acid. pH at 7, neutral. Now, what do I do with these other ones? Well, that's where it comes down to, I got to do those calculations. So the calculations that are important to us, pH is the negative log of H plus or H3O plus. POH is the negative log of OH minus. And pH and POH add together to make 14. So in letter B, I'm given the concentration of hydronium. So the negative log of 1 times 10 to the negative 8th would give me a pH of 8. So yes, the question was, could you just look at the exponent here and know what it is? And the answer is yes. If our coefficient is 1, then all you need to do is look at the exponent and it'll tell you the pH or the POH. Now, if it wasn't 1, then you'd have to put it into that equation to get a much better sense of what it is. Could you probably guess your way around it? Probably. So this is a pH of 8. pH of 8 would be basic. Using the same kind of logic for letter F, we've got a pH of 12. So that would be basic. For letter E, here's where we can get a little bit tripped up. This is hydroxide concentration, not H plus. So that means that the POH is 10. And since pH and POH are 14, the pH is going to be 14 minus 10 or 4. So this is an acid. So, like I said, this is as far as the calculations really go for us for this chapter. Just being able to do these kinds of manipulations and kind of carry it through using these simplified versions of these equations wherever possible. And again, if you look in the textbook, you'll see that the examples are going to get more complicated because they're going to use numbers that are not this clean and friendly. And if you did come across one of those, I think I weed them all out, but if you did come across one of those, all you'd have to do is just use these equations and just slightly change your interpretation. All right, so we already kind of covered this, calculations inside of the pH scale using the negative log of the hydronium concentration. And what it allows us to do is, this is a table that you saw in your lab manual, where you've got the pH and its relationship between the hydronium concentration on one side and the hydroxide concentration on the other. The other kind of interesting thing to note is, again, if we're dealing with coefficients of 1 for these concentrations, notice how the exponents always add up to -14. So again, if you're looking for a kind of shortcut to everything, if I know that the concentration of hydroxides to the -9th, then that means that the hydrogen's to the -5th because the two have to equal out 14. So now we get into the stuff that you probably haven't seen, at least not that much of. You maybe saw a little bit of it in lab yesterday. We're getting into some reactions. Now, the most common reaction that occurs, at least from our standpoint, is in your stomach, the hydrochloric acid that comprises gastric juice is what is used to break down your food. Here are some general reactions of acids. So generally speaking, acids will react with metals. When they react with metals, they will produce salt and hydrogen gas. They will react with bases. This is a neutralization reaction. In a neutralization reaction, bases react with acids to make a salt and water. And so what happens in the process is the hydrogen and the hydroxide basically cancel each other out. That's why it's called a neutralization. And then finally, acids will react with bicarbonate and carbonate ions to produce carbon dioxide gas. And so what's happening in both of those cases is the acid is reacting with either of these and making carbon dioxide and water as the products. So this is an alternative form of a neutralization reaction that forms, instead of a salt, it forms a gas. The gas in this case is carbon dioxide. Just as a reminder, for these first two types of reactions, when we say salt, we're not necessarily referring to sodium chloride specifically. What we're referring to is an ionic compound that has neither hydrogen nor hydroxide as one of the ions. So here are some examples of acids reacting with metals. Now, acids will react with a variety of different metals. There are only a few metals that acids, in fact, will not react with. Those metals are what we consider inert metals, and they mostly are composed of the precious metals: silver, platinum, palladium, gold, things that are a lot harder to come by, but generally hold up pretty well to acid resistance. Usually when we talk about acids reacting with metals, we're talking about things like potassium or magnesium, aluminum, iron, in particular in steel, tin, zinc. And again, these end up producing a hydrogen gas as a byproduct and some kind of a salt. So here we got an example of hydrochloric acid reacting with two different types of metal. Basically, what we see happening, this kind of reaction has a name. It's called single replacement. But basically what we are seeing in each case is the metal is changing places with the hydrogen. That's how we get the hydrogen gas. And then the metal becomes ionized and forms a salt. Now, we won't see those salts unless we evaporate all of the water. Because remember, the acid is an aqueous solution. It's dissolved in water, and the resulting salt product is usually soluble in water as well. So in these kinds of reactions, we wouldn't tend to see the salt forming unless we boiled off all of the water, and then we would be able to see it. In neutralization reactions, we have acids reacting with bases to give us salts and water. And again, what we're talking about primarily, that hydrogen reacting with that hydroxide, that's what's going to come together, H plus OH, to give us H2O. We've seen similar reactions to these when we did things like esterification reactions in organic. Now, this is not an esterification reaction because we're not making an ester, but we are creating a water molecule here just like they did in those reactions. And it is coming from the H and an OH coming together. The salt here, in this case, is sodium chloride. It's the leftover of the acid reacting with the leftover from the base and giving us an ionic compound. And just like the last one, that ionic compound is usually soluble in water. And so we're not going to really see it forming unless we do something, oil off the water, or we add some kind of a chemical indicator to let us know that the reaction actually did occur and that there was a change in the solution. And that brings us to titrations. Now, you will do a titration next week in lab. Titration is a laboratory procedure. Has anyone ever done the titration? Okay. So basically, what happens in a titration is you've got an acid solution and you've got a base solution, and you set up your acid usually in some kind of a flask or a beaker, and you've got your base solution in some kind of large container that you can add small amounts of in a given amount of time. So the technique, the equipment is usually a burette. But what it does is we can use that small addition, little bits at a time, to figure out the relationship, to figure out the exact point of neutralization between the two. Problem is, acids are usually clear and colorless. Bases are usually clear and colorless. And the product that they make, water, clear and colorless, and salt solution, clear and colorless, it's really hard to tell when the reaction is actually doing anything, let alone when it's done. This is where an indicator comes in. An indicator is usually some kind of a dye, some sort of organic molecule that is pH specific, meaning when the pH is in a certain range, it will appear as one color. If the pH escapes that range, it'll appear as a different color. Now, in the case of phenolphthalein, the pH of that indicator is colorless in all acidic solutions. In all basic solutions, the pH of that indicator is kind of like a bright magenta pink. And so the trick to a titration is adding just enough base to the acid so that pink color barely starts to appear. Because the more base we add, the pinker it's going to get. And the more we can say that we are over where we should be. So the titration itself, it's an interesting technique. It's something that, you know, if you have to do it, you get used to it. It goes kind of smoothly once you do it a few times. If you're only doing it once, it can be really frustrating to have to do it that one time and get it right that one time. So this is what the experimental setup looks like. And again, you'll be doing this in lab next week. And so you can see you've got an acidic solution here in the flask. This is your burette filled with base. Doesn't show up super well in the photo here, but you can look closely and see that each one of these marks, each one of those volume lines is very heavily marked. We can actually measure pretty precisely using a burette. Where you can see that not only is each milliliter marked, again, probably hard to see here because it's a little bit blurry, maybe a little bit better on the individual slides, but you can also see that each 1/10 of a milliliter is marked as well. So we can read this really, really precisely, which allows us to do things like solving problems, like trying to figure out concentrations. If I know this concentration really, really well, and I know how much I use, I can use that information to figure out the concentration of the acid, or vice versa. Brightness of this room is not doing the picture as much justice as what is necessary. If you look closer, you can see here that this part of the flask, we are starting to just see some pink here, which would indicate that the reaction is proceeding, but that it's not actually finished. When the reaction is finished, you get this, and the intensity of this color depends upon how much of the indicator that you use. The more that you use, the more stark it's going to be, the more intense the color is going to be. But this solid pink color is what you're looking for. You're looking for the first appearance of pink that is consistent, that stays in there once you do the titration itself. That is what is known as the endpoint. And at the endpoint, this is when you can do some of those calculations that I talked about. So a little bit of a heads up about that, because again, you are going to see that in lab. You are going to be asked to do a titration in the lab, and that's what we're going to go after there. All right, last concept here in chapter 10, buffers. Buffer solutions are interesting because with a buffer, what we see is the ability to heavily regulate pH changes. So let's take water. Water, neutral water, should have a pH of 7.0. Add even just a little bit, couple of drops of acid to that water, the pH of the water is going to change drastically. Add a couple of drops of base to that water, the pH is going to change drastically. Add a whole lot of either one, and you're going to see the extreme sides of the pH scale, 1 and 13, 0 and 14. But with a buffer solution, when we do the same thing, look at the difference. We started at pH 7 here, we added some amount of acid. The pH went all the way from 7 to 6.9. Added some base, pH went from 7 to 7.1. How? Why? What? Well, something is going on in here that isn't present in here. A buffer is able to regulate pH because it contains a combination of what are called conjugate pairs. So if you remember from the video, I talked about the idea that you could find a characteristic mate on the other side of the equation that was different by an H plus, one direction or the other. So water had hydronium on one side and water on the other. Ammonia, NH3, was NH3 on one side, NH4 plus on the other. That is what is called a conjugate acid-base pair. And in order to create a buffer, you need that conjugate acid-base pair. But it can't just be any conjugate acid-base pair. It has to be the conjugate acid-base pair of either a weak acid with its mate or a weak base with its mate. The weakness is important because in the weakness, we have reversibility. Remember when we talked about with dissociation, weak electrolytes, the idea that a weak electrolyte only partially splits. Some of it stays molecular, some of it ionizes. If I have a strong acid, there is no reversibility. It's a complete dissociation in one direction. I'm not going to be able to turn that chloride ion and add an H plus to it to make it HCl again. It's going to go right back to being chloride and H plus. So a buffer takes advantage of that reversibility inside of that weak acid or inside of that weak base. And what we see in the most effective buffers is that we have a similar concentration of both. So if I'm looking at a buffer combination between acetic acid and the acetate ion, what I'm going to see is that inside of that buffer, I have similar concentrations of acetic acid and sodium acetate or potassium acetate or whatever the source of my acetate ion is. I'm going to have both present and both present in relatively constant, consistent amount. It's not going to be one-sided where I've got a ton of the acid and just a tiny little bit of the conjugate buddy. They need to be near each other in concentration. Because what's going to happen, why these pH changes are going to be so moderated, is based on the relationship between those two components and each other. Here's what happens. Here I've got my conjugate acid. acetic acid. In that reaction, the acetic acid is going to take up any hydroxides from a base. And what's going to happen is it's going to do a neutralization reaction. Hydroxide steals that hydrogen, turns it into water. The acetate ion gets created as a leftover. But notice that in this reaction, not a whole lot changed. I don't have any extra hydroxides floating around. I don't have any extra hydroniums floating around. The pH is going to remain relatively consistent. Now, adding that base is going to cause the pH to go up a little bit, because this conversion of acid to conjugate base does have a slight impact on pH, because we're going to have less acid available to make hydroniums. But the difference is going to be slight enough that it's not going to be super noticeable. We'll pick it up, but it won't be going from pH 8 to pH 12. It'll be going from pH 8 to pH 8.1. And in the opposite circumstance, if an acid were added to my buffer, the acetate ion reacts with that acid, creating acetic acid and water. And notice again, the net effect here. No extra hydroniums, no extra hydroxides. The only thing we're seeing is a slight increase in the concentration of the acetic acid, which means we're going to see a slight lowering of the pH because we now have more acid present in the solution to dissociate. But this is why we have to have these in relatively close concentration with each other. If it gets too out of balance, then eventually the buffer is no longer going to be able to self-regulate. If I add enough acid to this, to completely deplete the acetate ion, then at some point the acid concentration is going to become so great that I'm going to see a spike in the change of my pH. But so long as I have significant amounts of both, I'm going to see that this buffer system is relatively well regulated and is not going to change in pH too much at all. But again, not everything can be a buffer. It has to be a specific combination. So with that in mind, let's look at these 4 possible examples. Could I make a buffer out of hydrochloric acid and potassium chloride? The answer in this case is no. I can't do it because HCl is a strong acid. Since it's a strong acid, it's a one-way reaction. As a one-way reaction, I can't get this reversibility with the chloride. The chloride's not going to be able to absorb extra hydrogen ions to reform hydrochloric acid, because hydrochloric acid, HCl, doesn't exist in molecular form in water. Automatically splits. Okay, carbonic acid and sodium bicarbonate. All right, this is a tough one, but it is yes. What we have to consider is that carbonic acid, when it reacts with water, is going to make hydronium and the bicarbonate ion. So this is my acid, and this is its buddy, conjugate base. If I have both of these present at the same time, I will have a buffer solution. All right, what about phosphoric acid and sodium chloride? Okay. Answer there is no, because there's no common ion. I would need some form of the phosphate ion here to make a buffer. Because again, I need to have some place for that back reaction to go. What about the last one here? Acetic acid, potassium acetate. All right, this one would be good. Acetic acid is a weak acid. And we can see acetate ion here. That would be its common ion. So the big takeaway here, if we're looking for common ions, if we're looking for potential buffers, for the salt, we really want to focus on this. Usually we want to focus on this anion. So if I've got an acid, I need to look at the anion of the salt. If I have a base, I need to look at the cation of the salt and see if there's a common thread between them. Is the only difference between acetic acid and the acetate the presence of the H+? If it is, then they're a conjugate pair. If it isn't, then we've got something else to worry about, something else to work with. Okay, so that's going to clear us up. That's going to take us